Okay. Well, welcome everybody. Thank you for being here. This is the last Inventors Gathering of the year of 2024. We have this every third Thursday, um, and it's very interactive. We encourage people to interrupt me or the speaker. A lot of times we have guest speakers, and to have a conversation about this. So I prepared a talk which was presented as about being about electronics and embedded systems, but I'd really like to make it a little more fun by imagining that you are a young Tony Stark. If you don't know who Tony Stark is, he's a fictional character who's an electromagnetic genius capable of making the exoskeleton that turned him into Iron Man. But if you want a real world example, you can imagine the inventor Jerry Ellsworth. You can look her up. She's sometimes known as Circuit Girl. Don't look up Circuit Girl because it has a different meaning unassociated with electronics. Um, and so what I'm going to do in this talk is to try to give you the tools that you would need to save the world by building an electromechanical gadget. Now, of course, I'm not going to totally achieve that, but that's what this talk is really about. So what I'm trying to do is to turn you into Tony Stark. And what we're going to do is describe the public invention devices, place these devices in a context as amateur research devices made with relatively little concerted effort and very little industrial design. We're going to talk about learnings in the modern technology landscape and the way the cost of various things have come down so much that a lot of design is now much more accessible than it used to be. And then we're going to talk about design principles, which of course is extremely subjective, but I'm just going to tell you what I think and what we've learned here, and then talk about the three skills that you really need to do this, which is a combination of software, printed circuit board design or PCB, and building enclosures. And if you can do all of that, then you can really do something awesome. So I'd like to talk a little bit about us. We are Public Invention. We're a US 501c3 public charity. We create teams to work on humanitarian inventions. Our motto is to invent in the public for the public. So we're creating inventions, but not purely in an entrepreneurial spirit. We're also trying to create humanitarian inventions. Public Invention right now could really use some donations, not necessarily because we're low on cash, but because we need to prove to the IRS that we're a public charity supported by the public. So small donations from the public assist us in doing that. So who am I? Well, I'm proud to say that I'm a public inventor. Not a very good one. I'm not a Tony Stark, but I invent things in the public interest. And so I'm claiming that title for myself. I am a public inventor, and I encourage you all to say the same thing. I'm also Robert L. Reed. I'm the founder of Public Invention. As I said, it's a US 501c3. I have a PhD in computer science. I was Presidential Innovation Fellow. I speak Esperanto fluently. I'm a little bit of a mathematician, etc. So I'd like to take a break from this scheduled talk and point out that we have a spreadsheet that defines 80 projects. I know this is going to be hard for you to read here, but we've got 80 projects that are all open source, free libre projects that you can work on with or without our permission. Some of these are ready to go. Some of them are not. A lot of them in preliminary states. Some of them have been done. On this spreadsheet, which you can't really read, we organize these by the category they're in, how easy they are to join, and the overall difficulty of the projects. Many of these are very difficult research projects. Some of them are much easier, and they span a wide variety of skill sets. But today we're talking about electronics. So when it comes to electronic gadgets, which more formally would be called embedded system, Public Invention has built the Polyvent Research and Education Ventilator, the Ventmon Spirometer, the General Purpose Alarm Device, an Oxygen Engine Digital Control System for NASA, which I'm very proud of, and an Oxygen Analyzer for NASA. So I'm gonna stop sharing and show you some of those devices, the small ones, when I get to them. So this is something that I'm really proud of. This is actually kind of the most important thing that Public Invention has done. It was not actually created by me. It was instigated by a teenager in Canada named Nathaniel Beshard and a PhD in physiology um, uh, from Russia and Germany. It is a medical ventilator, which is not FDA approved for use on patients, but it's a ventilator, as was, of course, a huge problem during the pandemic. So Victor and Nathaniel created this project. Public Invention absorbed it. Not all of the ideas in Public Invention are mine, although probably 60 of the projects on that spreadsheet are my ideas. And then over a very long period of time, with a lot of effort from Nathaniel, a bunch of engineers in Europe, a bunch of other people, including myself, we finally built a working ventilator. Now, what's impressive about this is the thing you're seeing right here is not one that we built. This was built by senior engineering students in mechanical and electrical engineering at Colorado Mesa University from the open source designs which we published. This paper has been accepted at Hardware X, and so within just a few days, you'll be able to see the 50-page paper that they used to build this. And so this is a tremendous success in the sense that other human beings have taken our design and have used it. In this case, it's only for educational purposes. The strange-looking tank they have on the left is something that Professor Thales Santos and Professor Michel Melantine work on there. They work on electrical impedance tomography. Those weird bolts in a circle around the thing are the electrodes. And when that tank is full of water, maybe full of water right now, and the air balloons are puffed in and out by the ventilator, the electrical impedance changes in a way that can be mapped to produce an image. In this case, it's a two-dimensional image, a slice of the moving lungs. And because electrical impedance tomography has two advantages, it's super fast and it's non-invasive. So it doesn't inject radiation or anything else into this. This can be done on the human torso or the human skull or some other thing. So it's an alternative imaging technology that they're working on, and they're using this ventilator both to teach their students and to simulate the actual breathing in and out of lungs within a simulated human torso for the purpose of doing research in EIT, or electrical impedance tomography. We've created the general purpose alarm device, which has been published at Hardware X. It's a device which I'll show you right here, but if you can see me in my camera, it's a little handheld device, quite attractive because of some designs that Lawrence made. And its purpose is to be an annunciator. So it screeches a really loud noise and flashes bright lights to get the attention of a human being. It itself does not detect any error conditions. It's merely an alarm mechanism, and another probably microcontroller system tells it that it's time to alert a human being to a problem. Now, that could be as simple as a cat has gone out a cat door, or it could be as complex as the patient's blood oxygen level has gotten too low and action needs to be taken by the medical staff. I'll stop sharing in a minute so you can see this device a little bit better. Another device we made is the VentMon, which is an open source, everything we do is open source, spirometer, and I'm holding it up here. Ben Coombs designed this little device. This is a 22 millimeter adult airway, and you can blow into this, and it measures the flow, pressure, humidity, and temperature of the breath stream, which is precisely what medical doctors need to monitor when they put a patient under ventilation. Now, in a sense, there's no longer a ventilation crisis. Let us all pray that the bird flu, which is causing serious problems with dairy cattle in the United States right now, does not cross over to human beings and causes uh, to be needed, but you never know. And then the most recent work we've done is to make what we call the ODICOS, or the Oxygen Engine Digital Control System. So that black case is a 6U rack, and what you see there is the Public Invention control system, which controls an ion transport membrane, which makes pure oxygen out of normal air for to be tanked for therapeutic purposes, or, since NASA's doing it, to fill spacesuits, or possibly on the surface of Mars to extract tiny amounts of oxygen from the Martian atmosphere to use as an oxidizer for a return trip from Mars, so that you don't have to take your fuel and oxidizer with you when you go to Mars. Now, I am not a chemist. Sadly, it's a science I'm not familiar with. So Public Invention has not made the ion transport membrane. Nonetheless, we've made this digital control system, which is very important because those things have to operate at 750 degrees Celsius. And so they have to be kept at a very precise temperature and loaded with exactly the right amount of electricity and so forth. And this project's a little interesting because this is a high power project, relatively speaking. It uses more than a kilowatt of power, whereas the other gadgets are small things. This on this tray here is the oxygen analyzer, which we have made for NASA and a Scottish charity called Kids OR, which stands for Kids Operating Room. It's designed to prove that the ion transport membrane system, which is made by a firm called American Oxygen, produces a given flow and absolutely pure oxygen over a 9-month test period. Our plan is to test this in Zambia and Scotland. So these devices are mostly research devices. We're not trying to make commercial products. We aren't doing industrial design. If we were graded on doing industrial design, we'd probably get an F. You know, we don't. These devices are modestly attractive, but they're not what you would call industrial quality design. We're really in research organization, and so we're doing either research devices or prototypes of open source devices which have never been made open source before. For example, our ventilator is not that interesting. It's not that different than other ventilators, except that it's the world's most open source ventilator. Also, a lot of the work we do is done with unpaid volunteers. We form teams of volunteers. Sometimes, if there's money for a project, they get paid, but a lot of times they don't. So I'd like to talk about our general, and everybody feel free to interrupt me if you have any questions about those things. So, you know, if you think about those things, each of those things is something that Tony Stark, the mythical character, you know, would have done in 10 minutes over his coffee break, right? But they're not shabby. You know, this is serious work that we're doing here. And this is accessible, you know, to anybody. And by the end of this talk, I hope you will have some idea how to go about making devices this good or better. So the design principle that I learned from Mr. Kent Beck when I was a manager at a software company is to use the so-called agile software methodology, except I'm applying it to hardware and printed circuit board design as well. And one way of thinking about this is that agile uses the idea that there should be no big design up front. The design is constantly changing, and there are principles. There are ways to do that, but the principles that are defined by the Agile Manifesto, this is copied from the Agile Manifesto, are quite relevant to what we're doing. Those are that individuals and interactions are more important than process and tools. We're going to be talking about tools in this talk, but really the tools are not as important as the cooperation of the team and the cooperation with the target audience. Working software, and I'm now adding and hardware to this statement, is more important than comprehensive documentation. customer collaboration is more important than contract negotiation, and responding to change is more important than following a plan. The whole idea of agile is that you can be responsive to a change, and that could be a change in what the world needs or a change because you've learned something along the way. So the idea here is to race to a minimally viable product, even though there is no product because we're not selling anything exactly. Although technically you can purchase these two vices and a polyvent at our store, at our website. Our purpose is not really to make money, but to produce devices like this, which can be ordered so that it makes it easier for engineers to reverse engineer, copy it. Of course, they don't really have to reverse engineer because all the designs are available freely at GitHub. But to hold something in their hand and decide if it's worth their time to try to manufacture the device themselves or make an improvement to it. And then what I always say, and it's been a long result of my career, but Kent Beck put it in words better than I can. What Kent Beck said is, to go fast, you take baby steps as fast as you can. You don't try to take giant leaps. You try to take little bitty steps over and over again and over again as fast as you can. And you work on your process and your team so that the team is good at doing small things extremely rapidly. Now, when it comes to making physical gadgets, or what would be called embedded systems, this is easy for hardware in 2025 in a way that it wasn't easy even in 2015. So first of all, 3D printing for enclosures. These devices are both, they have 3D printed cases, not injection molded cases, which is what you would do if you were making a very large number of products, is now cheap, fast, and easy. There are absolutely free of charge and also open source tools for making these cases. Both of these were done that way. I personally am more familiar with OpenSCAD, which is a 3D modeling system that's very friendly to computer programmers, but a lot of people like FreeCAD. FreeCAD is also parametric. FreeCAD is much more powerful in that it has a much wider set of tools available to it. Okay, CAD stands for computer-aided design. They do not deal with electronics. They only deal with the 3D cases or enclosures, for example. Okay. Now, many people now have inexpensive 3D printers, which are great. It's also possible to use online 3D printing services, which is what I use. So Xometry, spelled with an X, is a service which provides very high quality printing from anywhere and will deliver it to you in about 2 weeks. One of the reasons that I like to use Xometry instead of printing something myself is that you have a very wide variety of materials that it has available, including things like the plastic nylon and metal. So you can actually 3D print things in metal. And we have some projects where we're doing that, although we're not talking about them today. Now, printed circuit board design is also now cheap, fast, and easy in a way that I don't think it was. Certainly, it wasn't easy 20 years ago, and maybe it wasn't this easy 10 years ago. There's a program, there's several programs, but we at Public Invention tend to use KiCad. It's free, it's very good, very sophisticated as a design mechanism to build a design, and you just output the files and then you can send them to PCB houses or ordering firms that just allow you to mail in the files, sometimes populated with the components that go on the printed circuit board of the electronic design. Many of them are in China. Some of them are even in America. I'm sure there are some in Europe as well. And these allow cheap boards to be ordered and obtained in about 2 weeks. Okay, now perhaps I should point out, printed circuit boards are the way you make electronic stuff, and we're going to be talking about that a lot more. So what to be a little Tony Stark, what you really need is to be able to do these three things. You have to be able to do a little bit of mechanical design to make three-dimensional things like enclosures for your electronics. You have to do a little bit of electrical engineering to be able to make a printed circuit board, and you have to know some software. And when you can put those three things together, you really have a lot of power. You can make a complete device that can solve a real problem in the world, including a medical problem. Now, software, it seems like in a way it's old hat. I've been paid to be a computer programmer for more than 40 years. And in some ways it hasn't changed that much, but in other ways it has. And one thing that has happened that was not true when I was in graduate school is that there's now a huge library, if you will, of completely free of charge, but also completely free in the sense of free speech, free of legal encumbrances to use and to understand free libre open source software, which you can use as building components for your software system. Okay. I am not an expert in machine learning or artificial intelligence, but those fields have taken off in part because there have been very easy to use machine learning libraries made available for no charge for people to use. So in a way, because that corpus or body of or library of open source software is constantly growing, a computer programmer today is more powerful than they were 5 years ago. And it's really quite an extraordinary explosion in the capability of what you can do for 100 hours of programming. You can do more now with 100 hours than you could 10 years ago. So these are our free libre open principles. You remember, we are not like a startup firm. We're a nonprofit working in the public interest. So we believe everything should be open from day one. When we start a project, we create a GitHub repo that's public on the first day, even though it has nothing in it, and we just start building it up. Okay. And we call that working in the light. So we let people see what we're doing as we're doing it. We don't wait until it's finished or wait until it's good to show it to people. Now, in general, nobody pays any attention to what you're doing, but nonetheless, our policy is to always work in the light so that we commit to the publicly readable repo every single day or at the end of every work session. And we show our failures and our mediocrities without shame as well. So we think of ourselves as building a gigantic edifice or cultivating an Edenic garden, where everything we do is part of that very large thing which is being made to assist humanity. And it's not being made just by us. It's being made by people all over the world who are contributing to the free culture movement to make things freely available, both in terms of you don't have to pay for them, but also freely reusable from an intellectual point of view and a legal point of view. And our products is part of that. And I recommend that you, if you have a product and you're operating in this way, that you think in the same way. Now, one of the things that you have to do is to use appropriate licenses. I see that Eric Lund here from Sweden is here. What I'm saying is, of course, referring to US copyright law. I can't speak to the legal situation in other countries. When it comes to copyright, the United States is a member of the Berne Convention. And so that part of copyright law is more or less internationalized at this point. That was not true before 1983. So when we produce a hardware device, which has software and has documentation and sometimes has art and sometimes has logos and other things, we believe that different kinds of matter or different kinds of material deserve different open source licenses. Now, this is actually a repo at GitHub, the Public Invention license guidelines that anyone can see, and they can actually copy this repository as a starting point for their repositories. But as a rule of thumb, everything we do in software is covered by the Affero the GNU Affero General Public License version 3. That's also true of anything that's server or web-based delivered software. For hardware, we use the CERN Open Hardware License version 2, strongly reciprocal. For documentation, we tend to place it in the public domain because we believe that it makes sense for people to be able to, for example, translate the documentation without any legal encumbrance. Okay. On the other hand, we often write scientific articles, by which I mean peer-reviewed articles that are published in conferences or journals. And for that, we use the Creative Commons Attribution No Derivatives license, because a scientific work, unlike a piece of software, you shouldn't really be able to modify it. A scientific work is durable and permanent. And when you write a scientific paper, you're standing behind it, you're saying this is the truth, and unless you have to issue a retraction, it should not change in the future. Now, open source software and hardware designs are the opposite of that. They change all the time. They're living projects that need to change. And so that creates a little bit of a disconnect between scientific publishing and open source publishing. And then we do some different things for diagrammatic art. And we have actually attempted to create our own regulatory license, the Public Invention Sunlight Regulatory Agreement. But that project is stalled right now, so it's not really usable. So let's talk about design iteration as a principle and the first steps that a gadgeteer should go through. Now, there are different ways of doing this, but this is what we have found to be useful. I almost always start with an Arduino Uno. An Arduino Uno is a little credit card sized microcontroller. They're very robust. They're very cheap. They can do a lot. They're very versatile. When the Arduino was made open source, I think about 12 years ago now, the Uno was a revolutionary device, not because it was powerful. It's never been very powerful, but because it was open and simple and actually fairly rugged. It's hard for a beginner to break an Uno, and that's not true of other chips. So it's a great device for beginning your prototyping. And then, of course, we always start on a breadboard. And the word breadboard is a little bit funny, but it's a little device like this that you can plug jumper wires into. And so you can build a circuit without having to use a soldering iron or a printed circuit board. You just build it by just plugging wires into little holes. This is great for testing things. Now, jumper wires are very fragile. They come out a lot. And if, for example, a child walks by your project, they're very likely to pull the wires out, and then it's hard to figure out where to put them back. So it doesn't take very long before you say, we can't continue working on a breadboard. But even then, even when your project has a printed circuit board and is advanced, you may use a breadboard to design small changes or iterations or to test things out. And so being able to use a breadboard is a really fundamental skill towards doing the kind of electronics you have to do for embedded systems. So I always try to test the hardest part of the project first. So a lot of times, you know, for example, when we built this device, the hardest part was to get the flow meter here, which is made by the Swiss firm Sensirion, to work with the little bitty microcontroller that was embedded in there. So we worked on that first, and then the other sensors were relatively easy after that. So if you use this typical process, you start with an Uno and a breadboard. Right now, a genuine Arduino Uno R4 costs 22 euros. I'm not sure what the exchange rate is. And if you think about having some components that you put on there, it might cost $40 for one project, okay? You may then move to making a printed circuit board, but the printed circuit board can still interact with the Uno. Why? Because that's very convenient, it's very easy, and you can still add wires to the system. Normally, Public Invention orders 5 boards for prototyping, but 5 to 10 is kind of a breakdown, because whenever you order a printed circuit board, there's a setup cost. Usually it's about $100. But then after that, the boards are quite cheap. So if you order 5 or 10, the cost goes down per unit. Now the order will cost you $200, but of course you're getting 5 boards or more than that. So in general, the cost goes down per unit when you make a printed circuit board, even if you're using a relatively expensive Arduino Uno in the project. Now, as the project advances, you can make an integrated breadboard with headers, and that's what's inside this device if you were to take it apart. There are actually headers so that if you lifted the case off, you could plug it into a breadboard. That is not optimal if you're trying to optimize for cost, but remember, we develop everything in an agile way. So we want it to be adaptable until the very last moment. So by doing that, you have to pay for the extra headers. So it makes the cost higher than it would be if you were optimizing for cost. But by not having an actual Uno in there and taking the tiny little microchip that's part of the Uno and putting it directly on your printed circuit board, which is relatively easy with these new tools like KiCad, you can get the cost down to maybe $15 for a printed circuit board, as long as you're ordering 5 or more of them. And then finally, if you're really going to make a lot of them, you can optimize the integrated breadboard without headers and the whole system, and it might cost $8 per printed circuit board, including the microcontroller that's on it, to make a project. Now, I should go back and mention one thing. I sometimes use a soldering iron to make an intermediate step where wires are soldered together on what's called perf board or proto board. That makes a very rugged system, and it has the advantage that you don't have to wait 2 weeks to get it back from the site where you're ordering it. But many young people don't have soldering irons and they don't know how to solder. And it's slightly toxic because the solder usually contains lead and stuff. So many young people are simply never learning to solder, and they go right directly to printed circuit board design. That's a reasonable approach. It has the disadvantage that you do have that 2-week turnaround between when you make the decision, order it, and it gets shipped to you from China or wherever you're ordering it. So when it comes to PCB design, this talk is not a lecture on PCB design. Public Invention volunteers, Lee Forrest Erickson, Lawrence Kinchelow, Ben Coombs, Melanie, who's here, and Naram in Lebanon, are all perhaps more skillful than I am. But I am going to talk about some of our design principles, okay? So we iterate printed circuit board design just the way we iterate software, but a little slower. Usually we'll design, if we're really actively working on something, we might design a new board every 3 to 6 months, where of course we're changing the software every week if we're doing that. There are lots of online tutorials on how to do printed circuit board design. It seems at first like a dark art, but it's not that hard to learn. It's relatively easy to move from an Uno where which is a very weak microcontroller, to a more powerful chip when you go to PCB design, and to take it off of the little board that the Uno comes on and embed it directly in your own printed circuit board. Now, by doing that, the cost of that system, which might be 22 euros to start out with, goes down to just the cost of the bare chips that you need, which might be $1.50. So because many of the components on that Uno are designed to make it easy for an inventor or an engineer to use at first, the cost goes down tremendously if you integrate it into your printed circuit board. So the fact that these computers are relatively expensive, even if you're trying to make a product that costs, that you're going to sell for $10, you can start with an Uno that might cost you $30, because you're not going to end up paying $30 when you start mass producing them. Now, PCB rework is usually possible, and I'll do it, and I'm going to show you a picture of that. KiCad has a lot of great tools. I can't describe this as well as other people, but let me just say the way you use KiCad is first you write the circuit, or you write the sketch of the circuit, and then you do what's called laying out the board. And laying out the board is where the individual copper traces are actually designed. But the automated tools inside KiCad are so great that you normally don't put the traces down yourself. You just let it try to put them down. And then every once in a while, you have to move them because you don't want a high voltage line to be too close to the component, or some area of the chip looks crowded, or you want to put a bolt hole somewhere, and so the routes have to go around it, and so forth. But it's almost automatic. It does require you to manage a large number of things. So you have to be organized in your thought, but you don't have to be particularly creative. So this is an example of the rework that I talked about. This is a picture of the board that I made for NASA. And if you can see at the top here, the component labeled D2 was a Zener diode. And I made a mistake and touched a 24-volt wire to a ground wire and destroyed that diode. And it literally burned up and was destroyed. And then I tried to resolder a new diode in place. And eventually I failed so often that the little copper traces, which are these little lines that you can see under the green plastic solder mask, were completely destroyed. So I had to make another connection. This kind of beige or tan colored wire, I soldered in after we got the board from the factory. And so I looked at the circuit and said, okay, I need to make a connection from C7 over here to R35. And I literally just cut the wire to length, put it down, touched my soldering iron with a drop of solder here and at this connection here, and the board worked. So let me go back here. So one thing that's really important, and Lee Erickson is very much better at this than I am, is to design for debugging. Now, we use the term debugging to discuss software, right? Debugging is very important in software. How do you debug a hardware board? Well, the easiest way is to put little metal holes in strategic places so that you can use a device called a multimeter, which allows you to read voltage. Here's an example of a multimeter. And you can use these little probes that they have to touch parts of the circuit because they're exposed to see if the voltage levels are what they ought to be. It's a lot like debugging statements that give you visibility into something. Now, in some ways, electrical design is easier than mechanical design. But the problem is human beings can't see electricity. And so to us, electricity is a mysterious force, right? I mean, we didn't even know it existed until 1600 AD, maybe, but it's not that hard. It obeys laws, and actually it's much simpler than doing the mechanical design that goes into these cases. But you often make a mistake. And so when you get your board, if you can put probes onto it so that you can use an oscilloscope or a multimeter to see what's happening on the electrical system, which you normally can't see with your naked eye, then you can debug the board in a number of different ways. Now, a bug that manifests itself that way might be a software bug, or it might be a problem in the manufacturer. It might be that you thought this was a 5-volt line, but really it's connected to ground. And so it's never going to work as a 5-volt line. Or it might be something subtler than that. It might be that it's a 5-volt line, but it's too close to some other line, and so some electricity is being bled off due to some defect in manufacture. Or it might be that it's it's a 5-volt line, but it's carrying too much amperage for the width of the trace, and therefore it's getting too hot and melting. There are other problems that can occur. So intentionally add test points. Sometimes you can add 1 ohm resistors to allow current measurement. So a 1 ohm resistant doesn't decrease the current flow very much. You just put it in line, and then you measure the voltage across that resistor, and then that's the way you can measure current flow, which is harder to do in some circumstances. As you're iterating, you leave the headers in so you can add jumper wires until midway through your development process. Now, the headers take up a lot of space and they're relatively expensive, but they're great convenience as you're developing the system. One thing you want to do is to include indicator LEDs, which are under software control, including the built-in LED that often comes with the microcontroller that you're using, because a lot of times you may have some software problem that makes it difficult for your device to communicate with a host computer, like the powerful Macintosh computer I'm using right now to present this. But you can write a program that will blink an LED, and a human being can see it and understand that some condition inside the circuit by whether that LED is on or off or how fast it's blinking. An example of that is sometimes called exposing a heartbeat or a debugging pin. So if you expose a circuit and you don't even have an LED attached to it, you just make it go high and low once every second. If your project isn't working, you just put your oscilloscope on it or even a multimeter and you say, is that heartbeat ticking up and low? If it is, then I know the microcontroller is working. Now, I might ask myself, well, if the microcontroller is working, why isn't that light on that I want it to be on? Well, I don't know why your light's not on, but it's not because the microcontroller is stopped, because the microcontroller is successfully pulling that line up and down once every second. So you know the program is running. And little things like that can be very valuable. So when you have to rework a PCB, you might say, well, why would you ever do that? Why not just order another PCB? Because it takes 2 weeks to get a new one, right? I mean, if you're reworking something by modifying the board with a soldering iron or a knife, you probably have to modify your PCB design in the next iteration. But you don't want to wait 2 weeks to do additional testing. So if you just have a very sharp X-Acto knife, you can cut through a copper trace, which breaks a connection. And you can solder in new wires to make new connections. I misspelled new. And then you can desolder and replace components if you have to. Now, I'm not the youngest man in the world, and my hands shake and my eyes are bad. Desoldering components is uncomfortable for me. I really don't like doing it, and I'm not very good at it. And those little things are often very small. But you can do it. And if it's a question of trying for 30 minutes to do that and saving you 2 weeks of test time, it's often very valuable. So you can get away without thinking about an enclosure or more generally the packaging of your project for about the first 6 hours. And I mean that very literally. You know, you could just do a sloppy design with a rat's nest of wires on a breadboard and try to get something working. But that becomes so fragile and so hard to use that very soon you need to think about how to make it more stable, more secure, and less fragile. Now, sometimes you still use a breadboard, but you glue the breadboard down to, let's say, a sheet of plywood where you've also glued the microcontroller. That's a step. Usually you would use hot melt glue to do that, so it's easy to remove. And eventually, you need to create some kind of an enclosure because electronics don't like water, and they don't like to be placed down on pieces of metal. And even a human being's skin touching it could short to wires that shouldn't be shorted. So the general idea is you just close it in a way, and then even if some dust falls on it or something mechanically happens to it, it doesn't hurt the circuit and doesn't make it short out. If you make the first iteration, you still want it to be easy to remove the case. Okay, so this case, for example, has these little screws that you can unscrew it so you can test it, and you can try to test it with the case open. Now, why do you have to do that? I mean, of course, you would never want a user to have to do that, but you may have to do that if you're made some mistake and you're debugging something. So, for example, this is the third iteration of the case of the Ventmon. This is almost as small as this device could be made. There's not a lot of space left inside this case. It's got a tiny little LED display here, 3 buttons. It's got the air sensor, and the microcontroller is all in there. But we started with a design that was more like this size, because it made it easier to work with inside the component. In fact, I can take this apart. This comes apart really easily. So here you can see the actual electronic designs, and you notice it still has headers in there. Why? Because the LED still has to be attached to the header. The microcontroller is on the second chip. This is this lower part here is the electronic flow sensor. There's a tiny little plastic tube here, which goes to the pressure sensor, which is built on this printed circuit board. Ben Coombs made this device. I'm very proud of it. A woman named Loria Clark, who is now a artist, made the first version. It was larger, and then Ben made the smaller version. Okay, now when you make enclosures, for example, you can buy off-the-shelf enclosures. They're startlingly expensive, but when we made the first Ventmons, we used acrylic boxes that we bought off the shelf. Okay, they were quite expensive. They were like $70, but when you're prototyping, that's a reasonable thing to do. This design, which is quite nice with these little vent holes on the sides and the way it fits together with 4 pieces, was we used an open source case generating tool that allowed you to just say how high you wanted the case, what the dimensions were, and it just plopped it out. And then, of course, you have to cut your own orifices for, in this case, there's a liquid crystal display and these 5 LEDs on the side, and the 1 LED here, and the little button, and the little air holes for the speaker so that the speaker will be loud. So you start with an open source design, and thank whoever created this. I don't know who it was, but they created a design which we were allowed to modify, and it saved us a great deal of time. And then that's the reason why we work in the light. We benefit from this person having made this an open source design. We make our designs open source as well, in a way of giving back to the community. Sometimes people, may look at our design, they may not use it in the sense that they may not want to manufacture it, but being able to see it lets them make a good decision. So CNC in metal is now really awesome. We use the Send Cut Send program. You can make large projects that, for example, our work for NASA is dealing with about 1,500 watts of power, right? So it's got 110 volt mains power coming in, and it needs a fan and all that kind of stuff. And so it makes much more sense to use a metal enclosure. The photos that I showed earlier were created by Send Cut Send. So we designed a 2-dimensional shape, and then we ordered it in 1/16 inch steel. But all of the bolt holes and the little ventilation holes and everything were put in the design, and we just ordered it from Send Cut Send. 3 days later, we get a flat package. You open it up, and it's got a perfect sheet of metal, laser cut to your exact specifications. Okay, Send Cut Send can even do bending. It's a little harder to, that's trickier, but you can get bent metal parts. And so it's really a very economical way to get something done quickly. And it doesn't take long. So for example, for us to have made the same hole, the same system, drilling the holes ourselves with the drill press, which would have been an error-prone process, we could have done, but it would have taken many, many hours of work to do that. And the tolerances are really quite good in that. Of course, your design may be imperfect. We put some of the bolt holes in the wrong place. But that's part of the iteration of design. Now, I personally prefer OpenSCAD because it's really a CAD-based system in which everything is like a computer program. FreeCAD, on the other hand, is halfway between OpenSCAD and AutoCAD. Now, many of the college graduates who volunteer for Public Invention are familiar with AutoCAD, and I let them use it. A lot of times they have a school license, which will soon expire. And so it becomes a problem because we get a design in AutoCAD, and then there's no way for us to modify it without paying for AutoCAD ourselves. And AutoCAD, I think, costs between $500 and $1,500 a year. And so we in general have not purchased those licenses. We just use FreeCAD or OpenSCAD, which are completely free and very reasonable. Now, from a user point of view, AutoCAD lets you do a lot of things with a mouse or with a trackpad, and you're kind of molding it as if you were molding it with your hand. Whereas FreeCAD is halfway like that, but you do more parametric work. And with OpenSCAD, you literally don't do that at all. It's just writing a program to produce the shape that you want. But it works. So I've already talked about Xometry a little bit. It's similar to the PCB turnaround time in that if you make a 3D printed part ordered from Xometry or some other houses, there used to be a company called Shapeways that's gone out of business. Like, for example, we ordered this part. It does take about 2 weeks to get the 3D printed case, but it's a pretty reasonable thing. If you know someone has their own 3D printer, you can iterate the design faster because it only takes 2 hours to print something. Okay, so now we need to talk about software, which is kind of my bread and butter. That's what I'm best at. And I guess I need to speed up this talk a little bit. It's hasn't been that easy for Public Invention to find people who are good at software and good at hardware, electrical design. And so although I'm being a little facetious, if you can do CAD design, printed circuit board design, electrical design, and software, you have some superpowers, right? You can build a complete product from beginning to end, okay? Now, I use the Arduino IDE. It's a basic tool. It's kind of like the Uno. It's a great starting point. We use Platform IO for our larger projects. Once we get more than, let's say, 2,000 or 3,000 lines of code, Platform IO becomes more reasonable. Both of them allow cross-compilation to any, roughly speaking, any microcontroller that you want. So you can start out with an Uno, move to an ESP32, move to a Due, and of course, there are far more powerful microcontrollers than that right now if you need them. And basically speaking, that's a seamless process. The code that you write transfers from one to the other fairly easily. Now, there are exceptions. For example, interrupts are different on every microcontroller. So if you're doing advanced work, it's different. Power management is different on everything. Joe Hirschberger, who's here, has used a system called MicroPython. I have never used it. I always use C++. I suspect within the next 10 years, the number of people using what you might call high-level programming languages like MicroPython to program microcontrollers directly will greatly increase, probably go from 2% to 50%. But C++ is a sort of understandable lowest common denominator for programming microcontrollers. It would be rare that I would use C++ to program on a powerful general purpose computer. For example, I wouldn't do most scientific computations in C++. But it has advantages for working with a microcontroller because you can modify memory directly in a very reasonable way with C++. And I suspect even if you're using MicroPython or some other high-level language, you're going to have to know some C++ anyway. Okay, I'm going to speed up a little bit here. I prefer this simple loop architecture to ROS, or real-time operating systems. ROS stands for robotic operating system. I haven't used those other systems. it seems to me that in industry right now, opinion is split about 50-50 between trying to use more sophisticated operating systems and using what is called a simple loop architecture, or sometimes called a super loop architecture. I don't really have time to go into what the difference is, but they both require a great deal of discipline on the part of the computer programmer in a way that programming on a general purpose computer like a Mac or a PC or a cloud-based server does not. And as always, iteration and testing are key. It's very important at the beginning of your project to have a version number and print the version number out every time it starts up, because unlike in a general purpose computer program, it can be very confusing what version is actually loaded on the microcontroller. So you really want to do that. Now, there are ways to debug directly on a microcontroller, but I have never used them. I use the venerable technique that is sometimes called print lining. You just write things out with serial.print. So you sitting at your main computer with a little microcontroller beside you can see the statements come out. And those statements tell you what's happening inside the program. Now, because they can become so verbose that it's hard to sort out the information, I always use a debug level, which is a variable used to control the verbosity in each module of your program. Now, a trick is if your microcontroller crashes, which can happen, either because of software, usually because of software, or because of an electrical problem. Like, for example, if you do what in Unix would be called a segmentation fault, if you write into memory that you're not supposed to, you can crash a microcontroller. If you're debugging, when you crash it, it takes a little while for the serial buffer to write out to your main computer. And so sometimes it will crash and you won't see the last statement written. You can put in a delay of 10 microseconds after every print, and that will usually solve that problem. And then you take it out when you're done with it. Okay, I do this a lot. This is an example in our actual NASA code of setting the debug levels for each of the modules. So as you can see, I have different debug levels because depending on where I'm working, I have to set the debug level differently. If I set them all to high, there'd be so much information that I would drown in it. I wouldn't be able to see what I'm doing. So the debug level, often you just use either 1 or 0, but sometimes you have to have much higher levels. So there's a distinction between debug level 1 and debug level 2. 2 gives you more information, 3 gives you more information than 2, etc. Now, in my code, I have lots of debugging statements. And so sometimes as much as 50%, usually more like 25% of the lines of code in the program that I write for a microcontroller are actually debugging statements. And they look like this. You check the debug level, and if the debug level is turned on, then you print some stuff. Those things, this is a general purpose print, but it goes out to the serial port. So if I'm sitting there working, I will see the words fan inputs come out, and then I will see the PWM ratio and the revolutions per minute of the fan. Now, if I suspect there's a problem with the fan, I turn this debug level high and I get that information so that I can debug the problem that I'm working on. So in general, when you're working on a microcontroller, beginners use the delay function way too much. It won't take long before you have to do task scheduling. You really can't avoid it when working on a microcontroller. It can be done in a very sophisticated way or a very simple way. There are online tutorials for this. I don't have time to explain it in this talk, but you're going to end up having to do task scheduling. Now, one thing that's an important trick that is not at all obvious is most microcontrollers have a poorly documented macro available to tell you how much memory is left. Okay. Now, why is that important? Because the easiest bug to make in the world is to create what's called a memory leak, where you allocate memory constantly without deallocating it, which means over time, you're using up more and more memory. And when you run out of memory, your system crashes hard. Okay. Now, when you work in, as I do in Node.js or Python or Lisp or any other system that has garbage collection, you don't have to worry about that. But you're normally not doing that on a microcontroller. You're programming in C++. So it's a real problem. I avoid dynamic allocation of memory at all when I'm programming on a microcontroller. I just use static allocation. So essentially, the amount of memory is fixed when the first line begins by the compiler, and it doesn't change. And if it's changing over time, I probably have a bug in my code that will probably create a mysterious crash that will be very hard to explain later. Why? Because if you crash because you run out of memory, it doesn't have anything to do with the temperature you're measuring or the image you're trying to process. It just seems to fail mysteriously. And programmers should not be involved in solving mysteries, right? That's for detectives. So I always try to do the simplest thing that can possibly work. And that it takes some experience to try to discern what the simplest thing that can work is, but you always try to simplify things. It's like you have to be very clever and work hard to make it simple. Beginners work hard and make it very complex. And unfortunately, no one is capable of really maintaining that. Okay. Now, in C++, I find typecasting to be rather subtle. If you haven't programmed in C++, I probably can't go into it here, but a lot of bugs can be associated with the typecasting, which is necessary in C++, especially on microcontrollers. But in general, programming a microcontroller in C++ is not that different than programming anything else. So the same principles of good programming apply. And there are great books written on this. I've written one of them called How to Be a Programmer. But The Pragmatic Programmer is well thought of. The Gang of Four books, which is sometimes called Software Patents, Test-Driven Development. There are lots of books that will tell you how to be a good programmer. Now, you do need a lot of discipline. You need to use Git for version control, not just for your software, but for your hardware designs, right? And you really have to be careful designing version controlling even your enclosure designs. And one really valuable trick is when you get the boards back from the manufacturer, take a Sharpie and put serial numbers on them. You can either put a sticker on there or just write directly on the solder mask with a Sharpie so that you can see, so that you're building your own serial number system. Now, normally that's what a manufacturer would do. You might say, well, why does a hobbyist or a researcher need to do that? Well, it won't be long if you're designing your own board because you have a problem on one board and not on the other. And it becomes very confusing as to where the problem is. But you want to be able to put in your GitHub system, we had a problem with serial number 1. We didn't have that problem with serial number 2. Therefore, we're going to debug serial number 1 and try to figure out what's wrong with it. Okay. And as I said before, you should make your software report the version number at every startup of the program. We use issues in GitHub or GitLab to track our various to-do things. We prioritize them with boards. That's not a printed circuit board, but the Kanban boards, which are built into GitHub. And we coordinate using release milestones. Now, those are features in GitHub or GitLab, but they're very valuable project management features. Okay, so unfortunately, it's not enough to be smart. Like when I was in high school, in some ways I was smart, but I was not disciplined. I was not organized. Okay, I had to learn to do that. And you have to learn to save time by taking the time to be disciplined and documenting your stuff and organizing your work correctly. Raspberry Pis are completely different in that they are complete operating system based systems that run Linux, where they have their own process schedulers. They have memory management, a lot of very sophisticated things. They're wonderful. The fact that you can get one for $35 is just fabulous if you need it. But they bring with them complexity. If you don't need the power, Don't buy the complexity. It's easy to say, wow, I'll just get the biggest, most powerful computer I can for whatever my budget is and stick it in my project. But you're really costing yourself in terms of complexity if you do that. Don't let the perfect be the enemy of the good. This is fun. It's fun to build things. It's fun to be a maker. It's a real problem that is described in the industry as gold plating. Okay, that's a slang. We're not really gold plating anything. But a lot of engineers just want to keep making it better and better and better. And they never get the project done because they just keep making it fancier and fancier. Instead of doing the simplest thing that can possibly work, they do the fanciest thing as if they're trying to impress their friends with how smart they can be or something. You know, I applaud people wanting to do a good job, but you do a good job by being simple. You don't do a good job by adding things you don't need. Okay. Everything that works is better than vaporware. Okay. Vapor is a slang term for meaning software that has not yet been written. The worst program in the world is better than vaporware. Companies go out of business because they trust a large company like Apple or Microsoft to produce software that they depend on. So what they're doing is they're making a business decision based on vapor, on a promise that something's going to be released in the future, and it may not be. And that's the end of the company. In the same way, if someone tells you, I'm going to write this piece of code and it's going to be great, it's way better than what you're doing, believe it when you see it. Don't make decisions based on vapor. And this gets to the next point. Speed is the essence of learning. What you're trying to do when you're iterating is learn as fast as you can. You're trying to take baby steps, each of which teach you something. Often teaching you is, can we use the flow sensor? Yes. Can we use the pressure sensor? Yes. Can we use the temperature sensor? Yes. Can we make it in a smaller package? Yes. Can we shift from an UNO to an ESP32? Yes. And you just build up the project that way. If it takes you a long time to learn things, you're doomed. And that's why I say you should take baby steps as fast as you can. Okay, we haven't touched on power engineering, like building machines that take hundreds of watts of power. We haven't talked on using batteries, which is more complicated than you might think, using Wi-Fi and Bluetooth, which I've done quite a bit of, using AI image processing, sound processing, digital signal processing, which I have not done very much of. I used to do some acoustic digital signal processing and sensor design. We don't have time for that. But now I'd like to summarize this. So using completely free tools and free software, it is easy and cheap to prototype sophisticated devices or gadgets that would have been much harder to do 20 years ago. There's an open source body of code, an open source community, open source tools, and many tutorials that give the maker, inventor, hobbyist, designer, engineer unprecedented power. You can do more today than you could 5 years ago. You need a team that has the trifecta of skills. You have to have some computer programming. You have to have some PCB design, which is normally part of electrical engineering. And you have to have enclosure design, which is part of mechanical engineering. If you have those three things, they don't have to be in the same person, but you have to have those people on your team, then you can build anything. So my question to you is, what will you do with your new power? And that ends my talk. I'm happy to entertain questions. We try to make this very interactive here. Now that I'm not sharing, it might be a little easier for you to see the Ventmon. This is the Ventmon gadget that we made. This is a Wi-Fi enabled device. It's very small, but it's enabled with Wi-Fi. So when you turn it on, you can monitor the waveform that you produced over the internet. This is the general purpose alarm device. I'm not turning it on right now, but these lights are are surprisingly bright, these little LEDs. So if you mount this on the wall and it starts screeching at you and these lights flashing, it will get your attention. Almost if you're in a different room. It's not quite as loud as a smoke alarm, but it's real close. It's lovely to see some people I haven't heard from before here. Thank you, Gautam Adabala, Vaibhav Durgasi, etc. Anyway, I'm ready to take questions if anyone wants to has a comment or a question.
Yeah, I think a good one to start with, Dr. Reed, would be, do you have any recommended tutorials? I know you talked about there are a lot of free online sources for where to start with some of like KiCad or some of the different software that someone would have to learn, right? Like how to utilize to design their circuit once they have a schematic. So what would you recommend? Like what are some accounts that maybe you subscribe to that you're like, hey, they're pretty good. They're pretty great at walking someone through any educational gaps you have with KiCad or Opens like SCAD or OpenSCAD.
So I'd have to do a little bit of Googling to answer that. I believe Lee Forrest Erickson would say that Robert Frenick has made very good tutorials for PCB design using KiCad. I think that's the name of the gentleman who's done it. We often use tutorials which are called Random Nerd. So there's someone makes something called Random Nerd tutorials. Those are often very good. I look at, for example, if you just look at YouTube and you search for OpenSCAD tutorial, you'll find a lot of tutorials. You sometimes have to try them out. They don't always match your level before you find one that you like.
Mm.
But they're available. Go ahead, Melanie. I see you have your hand up.
Yes, I have a couple for you actually. His name indeed is Robert Frenick, and I'm going to give you all the links in the chat.
Okay. Yeah. So Melanie has learned PCB design in the last year and a half. She's made a device I don't have right out on hand right now. It's still being designed. But and she's iterating the design, in fact, right now. It looks like Eric has written a lot of valuable things in the chat here as well.
So the links I put in, they go from top to bottom, least
Okay.
most beginner to most experienced, and then the last one is a couple books, but I think for beginners, the books are a bit
Okay.
challenging. Yeah.
Yeah, I guess probably the gentleman pronounced his name Robert Ferranick, not Frenick. I may have said it wrong.
Exactly. Okay. Also, Megan, if you want to work together or see a PCB in action, I can show you the moon rat.
Yeah, I would love that. I'm definitely interested in knowing more about how to do the raw PCB because most of my projects have been like microcontrollers or like breadboard designs that were really basic with enclosures. But they never really went over the how to go from schematic to an actual like PCB manufactured. Like they always felt like you should outsource that for group projects in college, which I felt like didn't match industry level standards, which made that kind of a learning gap, at least
Right.
for my program.
Go ahead, Eric.
I'm listening with interest. I have some observations that I might discuss with you as well, Rob, because I don't know the audience and so on. I worked for the last 15 years on how to make electronics design like extreme programming, in a sense, in industry, in order to get thousands of more engineers able to go from ID or need to production, not just product. What I mentioned how in any engineering organization that you look at, could be the most famous aerospace and so on. There are parts of it that work in a certain way, maybe pushed by the organizations they work with, customers or funders and so on. And then there are other part of the same organization, but sometimes they like to talk about more, like Skunk Works with Lockheed Martin that I made some references to. The thing that you, with all methods, if you don't have knowledge, build a knowledge base over time, then you have nothing to draw from. So to me, my message after 45 years as in engineering is it's often overlooked, and it's nothing but criticize public invention, because I think public invention especially is working on building the knowledge base that we need to, in a inspired moment or in a crisis, in a dire times, being able to draw from a broad, from superpowers, as Robert puts it. If you, I'm a board member of a national Makers of Sweden, for instance. That's not something where I think the maker movement today is the best things in sliced bread. It's just that taps into one aspect of where people try to organize and learn. They are not collaborating as much as we would like, but that's, on the other end, I work with aerospace companies, and they are sometimes interested in working in these ways with Skunk Works or whatever agile. But what I look at is the problem is that if you involve subcontractors or anything in when you need try to realize fulfill a need or realize an idea, you often end up with people who only have an incentive from making more hours. And what we look at is how to be more effective, not efficient.
Yes, yes.
And then it's more of modules. It might be overkill to use a Raspberry Pi, but if that makes sense sometimes, that's a thing. But you need to be multi-talented or multi-clued in on things. What can you do with an Arduino? What can you do with Raspberry? And usually when you're young or inexperienced in anything, and there is excellent work done on this in the Dreyfus skill acquisition model, you tend to just follow a pattern. You tend to say, I use Arduino, or I use Raspberry. I listened to someone who said that Arduino was better than Raspberry because it had more pins, and that was one perspective on it. But that guy was doing robotic lawnmowers in an excellent way, but he had that perspective on things.
Right.
Well, I think KiCad is the way to do things, but you need to understand that there is something you need to learn by capturing and designing something as a schematic from a breadboard. Then do it, learn that in order to place component on a PCB, you have to do some work on understanding that it's taking something which is a principle work, how it connect things, to make that into something that is manufacturable. There are some manual work in that, but without that manual work, it's hard to make a working design. Right. I listen a lot to the Amp Hour podcast, but that's semi-professional, but it's useful for learning about it's one of the most popular podcasts on electronics design with two engineers, and they usually have people from the industry commenting on everything, like what Robert was talking about, but going into the things that are manufacturable at scale as well.
Right. Well, so I know I haven't addressed manufacture at scale. That's sort of a different topic, but I think you've hit on something very important. I'm in favor of humanity as a whole planet coming together to cooperate on things. It may take 200 years for that to happen, but open source allows larger teams in a way, without even knowing each other, to cooperate on things than they could before. But you're right. If you don't have the expertise concentrated in a small group of people, right? And the joke is that the team has to be, you have to be able to feed them with one large pizza, right?
Yep.
You know, then if you can get the team that small, then the communication can be very tight within that team and they can go very fast. Whereas, you know, and God forbid you have to do it in the US federal government, but if you have to get a subcontractor to do something, just the time it takes to negotiate it, even if it's reasonably priced, even if they do a good job, slows you down so immensely. Okay, now I should point out, I am probably not a good PCB designer, but I know a little.
But you're developing the skill.
Right. And if I had to hire someone to do it and they tried to trick me by saying something's going to take 3 months or something, I say, I know it's going to take 3 days. You know, I know that. I couldn't do it, but I know it's not a big
The
deal.
problem, Robert, is more subtle than that, because it's not that they trick you. They drive the work in the direction that gives them the more hours. Maybe not consciously, but I've learned from all subcontractors, from single person to large organization, they want to do a unique and optimized design for every customer to create as much patentable blah, blah, blah. That's often translates to magnitudes more R&D, and then the whole product to be economical is pushed to low-cost manufacturing. When we talk to people that run assembly factories like electronic manufacturers, they try to avoid these days, if they are in high-cost countries, try to avoid involving design consultants and try to find solutions where people who have a need or an idea can do it with modules, because a transaction through the factory is what runs their business, not the actual things put on the board.
Right.
And the importance of PCBs, of course, I usually talk about the difference between the 2,000 kilos of electronics that was guiding the Apollo carrier rocket, and the same function in 35 kilos, mostly aluminum casing. We needed 2 more of those in the Apollo project, and through PCBs, using PCBs instead of wires and metal frames to put it on, you got the same function as 2,000 kilos of old TV equipment technology for the guidance system. They made 2 more, each was 35 kilos.
Right.
And they were guided by the people like Fred Brooks, Dave Parnas, and Margaret Hamilton.
Yeah.
Which was the people that said that software is also engineering.
All right. Well, let me see if anybody else has a comment or a question here. I see Vaibhav, who made the oxygen concentrator in India, was here briefly, but I didn't get a chance to talk to him. Does anyone else have a comment or a question?
Yeah, I had a bad connection earlier, but yeah, I wanted to comment on the MicroPython and the approach to using that on Arduinos and whatnot. I picked that just as a opportunity to learn something new. I have several colleagues who have used it before, and I almost always do everything in C, in bare metal. And so, I mean, that's been my career for 20 years. So I found it, you know, I don't think I would ever use MicroPython for work, because it's always going to be a lot more embedded, a lot more purpose-built. But for an experiment, I thought it was a great opportunity to get exposure to that system and see, is it really, like, is it applicable to much, or is it really limited, or what's, you know, I just wanted to get some experience with it while doing something real. So that was the reason I chose it. It's not something that I use for everything or something, or that I'm familiar with. It was an excuse to learn something new.
Sure. But nonetheless, you know, wonderful people like Lemur Freed, who is also Lady Ada, make products that make it easier for hobbyists to do more powerful things. And I'm sure it's a case that 10 or 20 years from now, people will be programming, very powerful microcontrollers, and they probably won't be using C++ as much as they are today. Right. It makes perfect sense to make that, in a sense, easier the way Python and JavaScript and other languages have made programming general purpose computers easier than using C++. Go ahead, Eric.
MicroPython, you should know about Python, but Python is even people that build Python, and especially these people that work on performance of Python, they view it as a glue between C and C++ modules and Rust modules nowadays. So it's even on a microcontroller, it can be efficient if it's uses this usually C compiled modules, and you tie them together to test something. It might be harder to do TDD and debugging and so on, but that's another issue. But it's useful in many ways on a platform. And Raspberry Pi and Adafruit is in different efforts sponsoring MicroPython and Adafruit's Lemur Freed's Circuit Python. But
right.
they support it because they give back. Since they sell hardware and make money from that.
Yeah. Okay. Well, this has been a long session. I'm going to stop the recording now.